Hi guys, this video covers binary tree traversal implemented in a recursive way. So we're going to try to write code that performs the three kinds of binary tree traversal: preorder, inorder, and postorder. And for now, we're going to do this using recursion. We're going to use something called the binary recursion pattern. This is different from the linear recursion pattern that we've been using for a while. In linear recursion, in the general case, the function calls itself once, and that's why it has the name linear. In binary recursion, the function calls itself twice in the general case. This is a natural fit for binary tree nodes because a binary tree node has one pair contents, but it also has one left pointer and one right pointer, the two child pointers. So binary recursion is the idea that in the base case you don't do anything, but in the general case you make two recursive function calls, and that would account for all of the child pointers of a binary node. And so this binary recursion pattern fits that well if you want to do a recursive process starting at the root and working your way downward. Here's kind of pseudocode of what this would look like, just to kind of get that in mind. So a traverse function that somehow goes to all of the nodes in the tree starting at the root and working down would have the conventional base case that if the node pointer becomes null, return and don't do anything. That's what happens when we follow the child pointers of the leaf nodes down at the very bottom of the tree. We would call traverse on those leaf nodes with null pointers. We don't want to do anything in that case. But after we ascertain that node is pointing at an actual node, then we traverse the node's left child, and then after that finishes, we traverse the node's right child. So that right there is where the two function calls in the binary recursion pattern are. Let's recap what the traversals are. We can define them all in terms of this Euler tour. Remember that the Euler tour is kind of this blue shoreline contour around the binary tree, and following that contour can let us derive the three classical traversals: preorder, inorder, and postorder. The difference between them is whether we visit the node on the left side before we've gone past either of the two child pointers of the node, or on the underside of the node after the left pointer but before the right pointer, or on the right side after both pointers. And depending on which policy we take, we can derive the preorder, inorder, or postorder traversal. So preorder is what you get when your policy is to visit a node on the left side before the two child pointers. So if we follow the Euler tour here and visit on the left side, we would visit 7, 1, 8, and then 4. Inorder is what you get when your policy is to visit a node in between the two child pointers after the left child and before the right child. If we follow that policy on this graph, then we would visit 8, 1, 7, and then 4. And the third and final alternative is if you visit a node on the right side after both child pointers, and if we follow that policy, we would visit 8, and then 1, 4, and then 7. So what we're trying to do now is implement that visiting process in working code. So what I've done here is a first draft of taking that traverse pseudocode from a few slides ago and making this real code using actual data types and noting where we have freedom to put some code that does visiting. So I've got my void traverse function. The purpose of this kind of function would be to simply visit every node and do something there. It could be printing, it could be deleting, it could be iterating as an iterator, whatever. But we're trying to visit every single node and do something in a defined way. So the input to traverse is a pointer to a node that needs to be traversed. Initially, that would be the root. We have the conventional base case that if where is a null pointer, we stop, we don't do anything. If we get past that if, where is pointing at a real node. And if we wanted to, we could put some code here where this comment is to do something before either of the children have been recursively traversed. Then we do the first of the two recursive traverse calls on the left child. So this will recursively visit all of the left children of this node. And then in between that call and the next call, there's an opportunity to put some code there. That would be if you want to do something that happens after all the left descendants are visited, but before any of the right descendants are visited. So there's an opportunity to put some code there. Then there's the second of the two recursive calls that recursively traverses all of the node's right children. And then finally, there's another place where we could put some code if we want to do something after both of the children have been recursively traversed. And this fits pretty naturally into those three kinds of traversals. You might notice there are three spots where we could put code. In principle, we could put code in more than one of them, but for now, we'll just keep it simple. And if we put code in the first spot, we'll get preorder. If we put code in the middle spot, we'll get inorder. And if we put code in the third spot, we'll get postorder. So let's go through concretely what those look like. Here's the preorder traversal function. It's got the same pattern. We've got the pointer to a node in the same base case. And we do the visit operation first. Then we do a recursive preorder of all the left descendants. Then after that's done, we do a recursive preorder traversal of all the right descendants. Again, this visit is kind of a stand-in. That's not a defined function. That's just saying right here is where you would put the code to do whatever you're trying to do to the elements of the tree. Again, printing them out, freeing them, inserting them into another data structure, whatever. So if we were to run this, it would first be executed on the root node. And the first thing we would do is visit the 37. Then we would visit all the left descendants. There aren't any, so that would hit the base case and do nothing. Then we would visit all the right descendants. So what would happen on the 61? First, we would visit 61. So we did 37, now we're doing 61. Then recursively visit all the left descendants. There's only one of them, 55. Then recursively visit all the right descendants, 83. So the order we got here was 37, 61, 55, 83. And as maybe this is surprising, maybe not, that corresponds exactly to the ordering of the preorder traversal we get from the Euler tour. If we follow the tour here, we get 37, 61, 55, and then 83. It's the same sequence. We can get the inorder traversal by moving the visit operation one line down to be in between the two recursive calls. So again, same basic template here, inorder function, same kind of argument, same base case. First, this recursively visits all of the left descendants, then visits the node itself, then all of the right descendants. So if we run that on this same binary tree, first we would call the function on 37. The first thing it would do is visit all the left descendants. There aren't any. So the first element that gets visited is this line right here, 37. Then we recursively visit all of the right descendants. So the function call on 61 would first visit all the left, which is 55, then the 61, then the 83. So the order was 37, then 55, then 61, then 83. And that corresponds to the inorder traversal we get on the Euler tour, which would be 37, then 55, then 61, then 83. And postorder follows the same pattern. This is postorder, the title is off, but postorder is the same thing where we move the visit line of code to the last spot in the code. So same base case. First, we do the recursive postorder traversal of all the left children, then the recursive postorder traversal of all the right children. Then after that's all done, we finally visit the element itself. So if we run that over here, first we call postorder on 37. We would do a visit of all the lefts. There aren't any. Then we would do a visit of all the rights. Okay, so now we're doing postorder of 61. First 55 gets visited. Then 83 gets visited. It's these two lines of code on the 61 where. Then 61 gets visited, and we return from the postorder of 61. Then we're down on this line of code for 37, and we do the visit of 37. So the order of the visits would be 55, then 83, then 61, then 37. And that's what we get if we follow the Euler tour. We're visiting on the right side, so it would be 55, then 83, then 61, then 37. Let's make a few observations about this before we wrap it up. We are using the binary recursion pattern. There's exactly two function calls in the general case. There's a very clean, direct correspondence between the definition of preorder, inorder, and postorder and our code. Preorder is visit the element before either of its children, and that corresponds directly to putting the visit line of code before the two recursive calls. And the same kind of correspondence goes for the other two alternatives. So again, I would say this is pretty elegant. This code is pretty short and sweet. There's not a lot of kind of overhead or weird loops or anything like that. It's very short and to the point, and it's very easy to tell which kind of traversal you're doing just by looking at where the visit operation happens.